Hello, everyone. Welcome to this new IITT lecture, Interactive International Technical Talk, bringing together experts from around the world, young and renowned. This time is about TC220 on field monitoring and geomechanics. And I like to introduce the speakers. We have with us from Italy, Dr. Giorgio Pezzetti. He is the vice chair of TC220 with expertise in structure, instruments, monitoring, dams, tunnels, foundations, pile testing, environmental monitoring, a real true expert, geotechnical and structural, I should say. And Dr. Neelima from India, also expert in geotechnical, earthquake, engineering, microzonation, and site response studies, landslide hazards monitoring, microseismic data processing, and rock engineering. With us also Emma McConnell, very soon to be a doctor, expert in monitoring, desiccation, cracking, sensitive clays, unsaturated soil, soil atmosphere interaction, slope stability, and long linear asset management, field scale experimentation, and geomechanics. Welcome, all of you. I like to start by giving the floor to Giorgio. Please be my guest and share your screen.
Like to share.
And to all participants, feel free to interrupt. It's interactive. We are complementing the information for our viewers.
Do you see my screen? Okay.
Yeah.
Let's start. First of all, thank you very much, Dr. Ballouz, for this opportunity. Field monitoring in geomechanics is a very old matter, but we always need to improve it because it's something that has not been developed as many other activities in geotechnical and structural engineering. I will try to give an overview about the problem related to the activity of monitoring what we are doing in geotechnical or structural engineering. But before entering into the specific topic, I would like to I don't know why it's not, okay, sorry. I would like to say something regarding TC220, which is a relatively new committee of the International Society. It was established a few years ago. The idea came from Dr. Andrew Ridley. And at present, it includes approximately 61 members. I say approximately because it is changing. I don't want to say day by day, but every week or every second week, we have some new member. So at present, we have 61 members representing 26 countries. These members are divided in nominated members and corresponding. Nominated are the one who has been appointed by the National Society and has the right of vote what the TC is delivering. And the corresponding are members who can attend all the meetings, can participate in the discussion, can present ideas and suggestions, but they cannot vote. Sorry. Scope of the TC220 are mainly the organization of specialty conference, symposium, workshop, courses, and anything dedicated to the subject of field monitoring in geomechanics. To encourage the preparation of keynote lectures, state-of-the-art lecture on different topics, including new technologies, and the general report for conferences of the International Society and in other events. to promote the inclusion, and this is an important point we are stressing, to promote the inclusion of structural and geotechnical monitoring in universities and at conferences and meetings of other international bodies, thereby encouraging a common culture of learning through field monitoring. So this last point, I think, is one of the most important for the TC220. And indeed, the main scope is to advance in what we call monitoring culture. Culture means the ensemble of every matter related to monitoring. And we can say that the culture of monitoring is the common basis for being able to face and solve problems by identifying the most suitable solution and knowing how to understand the measures to evaluate, verify, prevent, and manage each specific solution. Why we are stressing this point? Because, and I will stress this during my presentation, too often monitoring is intended just as the use of an instrument, that means to install an instrument and collect data from the instrument. That's all. But it's something more. It's much more than that. And as we say here, is to solve problems. And this is the key point. And to identify the most suitable solution. These words, solve problems and solution, together with understanding what we are measuring, is the real core of monitoring. Monitoring not just to install an instrument, collect values, and present a table with a list of values. Is something more. And I will try to describe you what I mean with this. And so let's
Giorgio,
go.
I love what you're saying.
Thank you very much.
Because the experience I have in forensic geotechnics is mainly what you're saying. You know, they collect data and they forget it, whereas it's really there for you to solve the problem when it happens.
And it is, and this is, sorry if I continue, is for those who are working with monitoring, this is a very critical point because it could be a boomerang. Because if you just install an instrument, they collect a number and you provide a number, many times this number is not what the client is expecting or the engineer is expecting. And so we started the discussion, and at the end, the conclusion is, well, instrumentation doesn't work. We don't need them. Go on without it. So
Or
this
it's
is
useless. Yeah, well, I'm paying for it and I'm not
exactly. It's very
It's
expensive and doesn't provide for
should
any
be the
added
main
value.
topic of our talk today. Yeah.
Yeah. Okay. So let's see what is monitoring. This is a definition I found some years ago, and I think is correct. It is the repeated observation in time of a process or a phenomenon through the measurement of one or more indicator and the collection of information. What is important again here is to note that they use the word observation, measurement, indicators, and information. They don't talk about instrument and numbers and values. But I would like to propose you something more, and this is something I have prepared. And I would say that monitoring is the art of understanding the behavior of natural phenomena or man-made structure. And we will see why I'm saying that it's an art. And what the mission of monitoring? Again, this is a definition I found and I like very much because, again, said that the mission is to provide as much information as possible. And here comes a very important part, in the simplest and most complete form to be used by those who have to make decisions. This is the real scope, the real mission of monitoring, to support those who have to make decisions. And this is clear, for example, this is clearly stated in the observational method that is based on measurement and monitoring. But too many times we forget this, and we just provide for instrument, number, and values, not for information. What is information I am using as a term? Information is something more than data. It's the result of processing, gathering, manipulating, and organizing data in a way that adds to the knowledge of the receiver. In other words, and this is the key point, is the context in which data is taken. So again, not just a matter of providing values, but providing information, providing something more, something which helps those who have to make decisions. This is, to me, the key point. But again, we are talking about measurement. Monitoring is a time sequence of measurement, and observation. In some, well, sorry, probably you hear the bell ringing. The church is close to my house, so they are. But anyway, monitoring is a time sequence. So it's a repeated number of measurements, repeated in time, measurement and observation. But what is measurement? If we want to go in to the real meaning of the term, measurement, and I'm using here the definition given by the Italian standard UNI 4546, which says that measurement is an information consisting of a number, an uncertainty, and a measuring unit assigned to represent a parameter in a specific status of the system. So a measurement is not just a value, as we are used to consider. I remember when I was at school, they taught me that a measurement is just the ratio between two quantities, the reference and the actual quantities. Just the ratio is the measurement. No, measurement is something more, is an information which consists of a number, which is the ratio, an uncertainty. We have to know which is the level of uncertainty of this measurement, the measuring unit, of course, and the specific status of the system. We have to know the status of the system when we took the measurement in order to understand the value of that measure. What we can measure, or measurement can concern what? Of course, the effect, what we are looking for. And I here have some examples, some example: pore pressure, water table deformation, displacement, settlement, total pressure, strain, acceleration, whatever we want. We have enough instruments nowadays to measure almost all the parameters that we need to measure. But that's not enough. Again, we have to go more in detail. And I think it is necessary or mandatory even to measure the causes that have produced the effect that we are measuring. Otherwise, we lose part of the information. So we have to at least to know or to measure the loads, the pressure, the level, the flow, rain, wind, whatever has a consequence on the effect that we are measuring. But if we consider the definition of measurement, of course, we have to not to forget to know the status of the system. Status means the working program, the progress of the work, which level had been reached during the construction, for example, which boundary condition is
amazing.
a cold season, a hot season, raining season, whatever it is. Correlated activities. Are they excavating? Are they building? Are they vibrating?
I encourage everyone watching us to take a picture of this slide because it will save you.
aspect.
From
And
many problems.
And of course, the observation is not enough to measure something by instrument, but we have also to look at, to visually observe what is happening. So we need to perform visual inspection, manual check, test, collect samples, making laboratory tests, everything that can be useful in order to complete the information that we are providing for. And this is
Giorgio,
something. Tell me.
could you allow me to interrupt you for a minute?
Of course.
Just to give an example of a construction site in Manhattan, New York, where during the excavation they had done the piles all around, secant piles, to do shoring for an excavation. And as soon as I started, the building next door started tilting. So because they had a good monitoring system, monitoring all the structure and infrastructure around, they detected this movement. And they also had field reports, like what was happening, or if you have here work program. And the client asked, what's happening? Why is the building tilting? And all the teams at the site, like geotechnical engineers, structure engineers, the contractors start pointing fingers at each other. And nobody put together the work progress with the displacement measurements. And you could see that every time there was a jump in the movement, the drilling of the piles was done near the construction or near that building. And immediately we put together the reason. It was the construction, the drilling of the piles, and not the excavation. So please, field monitoring is so important, putting together the data so that people can see what's really happening. And this slide is so important because I've lived it and I've seen it and it helped me. Sorry to interrupt, but I had to say this
That's
experience.
important. And it reminds me another point I haven't touched in, I will not touch in this presentation, that field monitoring is a teamwork. Is the
Communication.
the instrument expert is not enough. The engineer or the designer is not enough. But if they put together, they sit together around the table, they discuss the matter, solution can be found.
Yes.
Okay. Which are the basic rules of monitoring? Let me say that until a few years ago, there were no rules. In geotechnical activity, maybe geotechnical testing, site testing, or lab test, we have a lot of standard, a lot of indication. We know exactly what to do, which instrument must be used, and how to interpret data. For monitoring, there were no rules. We started, I say we because I am part even of the ISO group who is drafting this standard. In 2010, we started drafting this international standard regarding monitoring. And this is the part one, which is the general rules. And here you can find a lot of interesting suggestions. But look, since this is a standard, it's not just a suggestion. It's something that you have to use, you have to apply, because it's a standard. But anyway, let's consider it as a reference mainly. And there are a lot of interesting points to consider. For example, regarding the instrumentation, they say that the key point in the monitoring program are the one that I've reported here: robustness, influencing factors, redundancy, stability, and function check and calibration. I don't go into detail of this definition. You can read it. But what I want to point out is that accuracy or error is not mentioned. That means that the most important point in a monitoring system or a monitoring program is not just the accuracy of the measurement, but is the robustness, is the influencing factor, redundancy, and whatever, because the conditions we are facing are so critical that accuracy comes later. First, this one. And I would add another 2 points, very important, which is the conformance of an instrument. Conformance of the instrument means that an instrument, when installed, has not to change the conditions. Otherwise, we don't know what we measure. And the classical example is the total pressure cell, for example. If in a situation like this, where we have a load applied to the soil and we want to measure the pressure at a certain depth, and we install a total pressure cell here, to install it, we have to remove the soil, to put the instrument, and close it. As soon as we remove the soil, we change completely the conditions. So what we measure, the pressure we measure, will never be the same as before. So this is important, the conformance of the instrument. And another one is the reliability. That means that the instrument has to work properly for the time that we expect facing the conditions that are expecting, and is working properly. For example, in a dam, if we have to measure, measure something here at the bottom, and we install an instrument here, which is here in the foundation, what is important is that he is reliable. It survived the conditions for the time, the lifetime of the dam, for example, which is 20, 40, 60, 100 years, I don't know, without major change in his properties. So reliability and conformance. But, and here I'm sure Marc will appreciate what I'm saying, there is another golden rule, which not comes from me, but from Ralph Beck. And he said that successful practice of engineering requires for high degree of engineering judgment. So we need, again, engineering judgment. We have rules, we have standards, we have references, but the main point is the engineering judgment. We have to know what we want to measure. We have to know the basic problem, the basic constraint. And we have to understand that we are measuring maybe in a small point, but the structure or the area is so large that we have to consider even a broader range. So Peck says that we have to know what is happening in the narrowest technical details and the broadest concept plan, in order to be sure that each step is sound. A small example, if we have a bridge like this, and you have to monitor, we can monitor, and could be important, a single node, and we have hundreds or thousands of nodes, but this is the node, but we have to not to lose the behavior of the whole structure. And nowadays, we have the instrument to do that. We have the instrument to measure the small detail and the entire structure, maybe using satellite or whatever it is. So this is another point that we always have to remind. And I found very interesting this graph. I mutuated from an Italian professor, Professor Cascini. I call zoom in and zoom out. So we have to consider the entire structure and then goes into detail and then back to the structure to see the interaction between detail and the whole structure. But I said it is an art. Why is an art? Because if we consider that there are no specific rules, no I would say academic references, what is called the human factor is playing a great role. Human factor can be related to engineering judgment, but it's something more. And human factor, to me, it is what makes the difference between a monitoring system and a monitoring solution. At the beginning, I mentioned solution. That's why. Here we have a couple of sentences from Elmo Di Biagio and John Dynamic referring to this. If you want, you can read it, but what the difference between a system and a solution? A system is something that starts from A and goes to B, following a straight line, a number of points, sequence of points, always the same and predefined. A solution is something which goes from A to B, but through a number of questions, a number of points where we have to consider different options, and in case we go back. And this is the difference. Too many times we see that what is used is a system, not a solution. And that's a point very interesting. Here, and even here, a very simple example, if it works. Imagine to have a river, and you have to cross a river with a bridge to connect point A to point B. We can build this type of bridge. It works, enables cars to cross the river, and it works, perfectly works. But it has, for example, piers inside the stream, inside the river. But we can even build something like this. So what's the difference between these two? The difference is, from a technical point of view, is that, for example, here we don't have any pier inside the river. That means that in case of flood, it is much better, much reliable. And many other things, but even from the point of view of the layout, is something much better. So this is the difference between providing a solution. We have connected A to B, and providing a system which connects A to B and provides a solution, which is something which implies more than just the connection of the 2 points. And again, using what Albert Einstein used to say, said logic and technology will get you from A to B, in our case, but imagination will take you everywhere. This is what we have to consider. But we have also to consider another point, that we are working in the real world. And the real world means that we don't have to strive for perfection. What we are doing, everything we are doing, is affected by error. So we don't have to strive for perfection, but accept uncertainties and error can be embedded in the measurements. We don't have to neglect it, but we have to learn and live with the fact. So again, I mentioned the accuracy. Accuracy is not the most important point. Error are always present. We have to know that there are, we have to consider, we have to live with them and learn from them. And as Benjamin Franklin used to say, don't fear mistake. You will know failure. Continue to reach out. So just to conclude, I will say that monitoring has to add to the knowledge of the receiver. Otherwise, it's useless. Monitoring has to be appropriate for both the narrowest technical details and the broadest concept planning. So we have to look at the detail, but even to the large scale. Monitor both effect and causes, as we've seen, as well as boundary conditions and, if you want, status. Provide for solution and not just for systems. And human factor is what makes the difference. Even if, as Andrew Ridley says, more often than not, the correct monitoring solution costs more, of course. And being prepared to pay more for a better product is another human factor. So you have to have a client or a counterpart which is prepared to pay more for having something more. And by this, I conclude, and I would like to dedicate this to these two pillars of our community, Elmo Di Biagio and John Dunnicliffe. I had the privilege of knowing them and working with them, and I have learned a lot from them. And what I have presented is something that directly comes from their minds. So thanks for listening to me. And now I leave the floor to Marc. And
Thank you, Giorgio. That was amazing. Thank you so much. Thank you so much. It's really, this global view was pinpointing to the way it should be done. I leave the floor now to Neelima. Please share your screen.
Yes, thank you.
I couldn't keep up, Giorgio, with all the quotes you put there, but I got some.
Is my screen visible, right?
Yes.
Your screen is perfect. Floor is yours.
I don't know. I'll just keep it down. Okay. So thank you so much. First of all, I should thank Marc for providing this kind of platform where like we can interact with everyone. And George, your presentation has given the base for me to take to the actual point which we are doing at the field scale, especially for developing early warning system for landslides. So my topic is on this is a completely research projects which I got funding from the Government of India. I'll be taking a case study and on real-time field monitoring that we are doing it for developing of the landslide forecasting model, especially to develop an operational warning system. I can say that this is the first kind of project where the real-time monitoring is happening in the country. Okay, so I'll just give you a background of my study region in a broader way. So India being such a diversified country with almost like, all sort of geotechnical problems we do have, and the landslides are almost like 13% of our Indian land mass. Such a big country, 13% is a huge land, is prone to severe landslides. In this year monsoon also, several areas have been prone to landslides. And coming to the diversity, especially the geological diversity that we have very younger, highly fragile Himalayan region, and wherein like huge amount of seismic multi-hazard, like seismic rainfall induced landslides. In addition to that, in the western part, so Western Ghats, where like we had IGC in Kochi, which Marc just mentioned, and that's actually what we call Western Ghats, and also Eastern Ghats, which are again prone to landslides. So, and Himalayas being that because of the tectonic activity is the very youngest, highly fragile, though they appear to be rock from little far. If you go, it comes out like a powder, such kind of very challenging, fragile material. And in addition to that, because of climate change, we do have this glacier burst and also huge climate change effect, like unpredicted rainfalls and highly urbanizations on the hilly infrastructure, that whatever happening in the country. And there is an increasing number of such disasters that we are seeing. Hope you might have seen some of the recent news where like almost 4,000 people have been evacuated or tried to evacuate in a place called Joshimath, where there is a huge subsidence of the ground in the state of Himachal. So this is actually my broadly what I'm doing since 2016. So these are my study regions where I'm working. Today I'll be picking up two interesting case studies. So one is like Joshimath, Uttarakhand, which is in the Himalayan region, and where we have done the combined hazard, and we had an extensive monitoring system on the real active landslide. And then other region which I'll be taking is on the Kalimpong. This is my first study region, which I got the funding from Department of Science and Technology, Government of India. So this is the first time in 2016 when I started landslide monitoring. So it is basically rainfall induced landslides. So both the case studies have a different methodologies and the approaches what we have done. So I'll briefly take you to the first case study, which is a Kalimpong. And this is in, we have done this in a local scale, because our goal for monitoring is not to develop the early warning system. Our goal for monitoring is to validate our threshold models so that we can reduce our false alarms. Because monitoring for a larger area is like very expensive, and also there are so many challenges like safety, communication, network. There are so many challenges that we face in the real field. So what we have done is like we have done this monitoring in a local scale, and then that we extrapolated this to develop the warning system in the regional scale. So this is actually the first project in landslide forecasting, and as I said, like this is supported also. And the adopted methodology you see here, it included only the temporal aspects of the forecasting, because the study area is in the local scale, and it has three aspects. One is like definition of the rainfall thresholds, and then installation of the field monitoring system, and the integration of these two to develop the landslide forecasting system. So, and then we collected the data in phases, like, we started with the collecting rainfall data. And when we started at this site, we didn't had any we got a rain gauge data or the rainfall data, which is giving us daily rainfall data, but we were looking for hourly data at least to develop our operational warning system. And then we put a lot of threshold models which are there available in the literature, starting from the conventional IDED thresholds, and then we done the probabilistic thresholds, and then sigma models. My collaborator from University of Florence, like, he developed that, and then we integrated that, we modified it, and then we use this field investigations also, like we had done DM maps, slope stability analysis. Then we choose installation of our sensors or monitoring system. In the monitoring system, we started with tilt meters, because most of the landslides in this region are shallow type of landslides. So we choose to go for tilt sensors, which are 2D MEMS sensors, and along with that moisture content sensors. And then we integrated that to do the performance enhancement of our rainfall threshold, so that we can forecast for a regional scale. So this is the methodology which we had done. I'll just take you to the details of the study region. So this is the location. It's one of the very beautiful area and a very tourist place. It's like a curved tabletop, the region, the town. So that urbanization is, you can see here, there is a lot of structures are built up, hotels of 5-story structures people are building up. Because of that, so they are blocking the streams, or this they call locally joras. So the streams, and then they are getting energy, and then there are a lot of erosion is happening when they are going down. So on this table, as I said, it's like a tabletop. On either side, we have two rivers which are flowing like this. There is Tista and a river Raleigh, which are very, very big rivers. And you can see here, this is the area where we choose to do the monitoring. To choose this area also, we have done a lot of field investigations and other things. And this is the only road that is there to connect this particular town from the rest of the country. And this has something like subsidence kind of failure. It's not a sudden failure that we observe in this region. It's like a very progressive sort of failure. So, and to start our work, like we started in the first step. Yeah.
What is the slope angle of this mountain?
Yes, it's around 45 to 55 degrees.
Wow. And what kind of soil is there? I'm guessing it's a conglomeration of cemented rock.
Yeah, it's the formation, geological formation is basically phyllites. And if you talk about the geotechnical base, mostly sand predominant, with some little percentage of clay also.
And was monitoring installed after the failure? And what kind of instruments was installed?
Yes. So the failure was like, in the western part, we instrumented that. As I said, like in that particular region, there are shallow landslides. I'll show you some of the photographs also for instrumented sites. So what we did is like we have put tilt sensors at 2 meters from the surface, because they are shallow, and we have done slope stability analysis to understand the depth of the slip circle, and then tilt meters have been instrumented. to understand the ground tilt, so that we can integrate that with the rainfall parameters.
So you were monitoring tilt with tilt meters and the water content with picnometers, or what kind of?
Yeah, volumetric water content sensor.
Okay. Yeah,
Shall
let's
I
keep
proceed?
going.
Sure. So then, the first, as I said, like we started with the threshold modeling. So in our first step, so we derived rainfall thresholds for the study region, starting from the ID and the ET thresholds, and then later ED thresholds, and also an algorithm-based approach called CPRLT. We use that for better efficiency. And both these thresholds, they consider the historical relation between the rainfall and landslides in the database. We had landslide inventory database, and a threshold equation of 5% exceedance probability was derived using frequently step approach also. So one-dimensional, two-dimensional Bayes theorem has been applied to do this probabilistic thresholds. And then we also applied the sigma model, which gave us efficiency. So it is an attempt was made to use this model, which is being used extensively in Italy for landslide forecasting. So we did this in an entirely different setting, and we go, since the collaborator, I know it, so we took the code and we modified it, integrated that with our real-time monitoring data also. So as the sigma considers the standard deviation values of the rainfall trend, both short-term and long-term, and then issues the warning based on different threshold levels. And this algorithm used for, customized in a particular case for this particular study area of Kalimpong. And then the second part is about the monitoring. So this is what the monitoring equipment, and this system, is developed at University of Tokyo, where I was doing my JSPS postdoc. So I took the system because I'm not into system development, but I want to use it for development of my warning system, to operational warning system for the study region. So this is the profile of the part of this slope where we instrumented this particular thing in the western part of the Kalimpong town. And these are the details of the sensors. So 2D MEMS sensors has been instrumented, and along with that, at each node, we had volumetric water sensor, and then they are communicating to the central unit. And then for every 10 minutes, we are getting the data to our server, which is in the central India, IIT Indore. So we instrumented this in 2016 post-monsoon, but since the pre-monsoon data we don't have, so we discarded that 2016 year. Since 2017, we continuously monitored for 4 years, and we tried, it's very difficult, at least in the first project we had so many challenges because some sensors could not respond, some sensors could fail in the second year. So a lot of challenges we could face in addition to other issues. And then we had a volunteer at the site, as George said, it's a teamwork. So we had, we took a volunteer at this particular study area, who used to send us a lot of ground signatures, photos and videos, something like this. So we tried to integrate to understand the behavior of the slope. And then when after started getting till data for continuously for 4 years, we tried to enhance the performance by combining these two. For this, we use empirical threshold, lag time, and critical rate as well. So this is the approach which we used it. So it was observed that integrating both rainfall threshold and tilt rate have the potential to overcome the limitations of both approaches. So when we use independently, so that's where we try to develop, and this particular system is in operation, and so this is actually the performance enhancement which we could do it with the real-time data. So further, the sigma algorithm was also modified to incorporate these tilt rates, what we observed. And sigma itself was performing well for this particular study region, Kalimpong, with very less number of false alarms. And the integration with the tilt rate further improved the performance. So we got almost efficiency of 0.94, as you see here, with a likelihood ratio of 20.23. And this method, we found it better among all the rainfall forecasting models that we explored for Kalimpong. Actually, because of time constraint, I didn't put it up, but we explored almost 8 different forecasting models on the same study region, which is again novel for this particular study. So 4 levels of warnings were designed for this study region in line with the existing warning system we had in the country. So with these color codes as like red, orange, yellow, green. So my second study region is a bit complicated because it is not only rainfall induced, it has seismic also, because this is very near to seismic regions in the Himalayas. So, and also the area is larger. And what we have done, we are working on two-stage landslide early warning system here, in which at regional scale, the system will combine seismically induced and machine learning based susceptibility maps with the rainfall thresholds, so that to give the real-time warning in susceptible region. Joshimath is a hotspot now. It's all everywhere in the news because of the 5,000 people have been asked to evacuate this year, but we started this instrumentation last year. And at the local scale, various thresholds will be defined from the data that's obtained from different sensors, and warning will be issued based on surpassing these thresholds. Here, the sensor system is monitoring system is a more complex. You can see here we had like weather station, we had tilt meters, accelerometers, extensometers, some of them below the borehole, inside the borehole, and some of them at the surface also. So we tried to integrate everything, and then we started working on that. And this particular system is completely in-house. So this is a recent land subsidence that we observe in Joshimath. And as I said, like almost 5,000 people have been asked to evacuate. It's a big challenge to even the government also to handle such a scale. So this is actually how we started. The probabilistic seismic hazard assessment for the entire Uttarakhand state, we performed to map the areas which are highly affected by the seismic hazard. Let me tell you my important challenge I felt in the last couple of years in monitoring was where to start monitoring, because in the entire state I had to find out the most vulnerable slope to put my instruments in that region. So that is more difficult for me. Anyways, we had a framework now, a comprehensive earthquake catalog was prepared, and then it was declustered, harmonized, and then completeness data was ensured. Then the study area was divided into 10 discrete seismogenic areas. So for each gene, then seismic parameters were evaluated using this catalog and of course the tectonic framework. So 80% of this entire Uttarakhand state is covered by the Himalayan mountain ranges. So we applied modified Newmark's model, and which incorporates the rock joint properties and employed in the analysis. So we found that this particular region of the Chamoli district, that is Joshimath, was highly susceptible to co-seismic landslide hazard. So this is the framework for physical modeling, and then to predict the regional scale landslide hazard for the entire state. And then, of course, as I said, like we also applied machine learning models for developing, landslide susceptibility maps so that we can choose the region. And then we started our instrumentation. So these are some of the details of the slope. We have done UAV survey. This is the actual slope. We have a village here. You can see here. This is the active slope. And this is the very important road. It's a it's a very important road, especially because we have very important pilgrimage just in these two places connecting this road. So every year thousands of people go use this particular road. So from both seismic hazard assessment and rainfall distribution, as I said, this is a multi-hazard problem. And it was identified that this particular region critically affected by the landslides. So based on these observations, we selected a site. It's a place called Lambagar. And so this is the road which I said, like, a pilgrimage road. And this site is a mixed slope with both soil and the rock. And meters, accelerometers, tensiometers, piezometers we installed in the borehole and at different locations. And then, cracks in the rocks are monitored using strain gauge and extensometer. And automatic weather station is also installed in the location. All the sensors, they are transferring the data every 10 minutes through VSAT. And the location of sensors are marked. You can see here on the figure. So this is how the data we are getting it every 10 minutes. We can observe that there are 1-2 degree respective increase in the tilt angle in the span of 8 months. And because we started this last year. And other tilt sensors are not there is no variation. And some tilt sensors, like especially 1 and 2, are the bottommost sensors in that slope. So which means that lower portion of the slope has started sliding down. So relatively, their values are higher. So at all 5 locations, wherever we installed rock joint extensometers and the strain gauge to monitor the extension and the strains in the rock cracks. So we can also observe that there is an increase in the crack width and strain with increase in the temperature also. So no significant correlation was found between rainfall and the crack width in this particular study region. Then this is the actual framework for real-time monitoring data. It's stored on the server initially, and it analyzes the rainfall data, then thresholds are crossed, and then it will send a notification. Then based on the rainfall intensity of that particular day, we perform the slope stability analysis using GeoStudio, and based on the crossing of the factor of safety thresholds, warning can be generated. So this is the actual slope profile, and then it is the location of the sensors that we did it. So 5 boreholes at different spacings, and then we did the numerical study using GeoStudio, and then profile of the slope you can see here under consideration. It has been extracted from the DM of that region, and groundwater table is initialized, and the transient CPH analysis is performed for rainfall simulation on SEEP-W, followed by limit equivalent stability analysis in slope-W. So this is the details of the slope stability. And you will get this kind of dynamic factor of safeties, which we can with the time. Factor of safety with time. So I'll just conclude it. We are trying to develop the landslide early warning by real-time monitoring, both in the local and the regional scales. And let me tell you, monitoring is a site-specific activity. Based on my experience, it needs a lot of inputs from geological, geohydrological, geotechnical, geophysical. Field test has to be carried out, and then a lot of slope stability analysis, both lab tests for collection of the samples, everything. After that only we can try to do the monitoring. So when we started it, like at some locations, we didn't get much data from sensors. So we have been very unhappy, and the safety was a major constraint. Because of attack of animals or some people, so many things, and communication system, very effective communication system, efficient and reliable communication system is another challenge. So multi-sensor based system can provide information on various field parameters, which we are at present doing in the Joshimat, and inclination and variation in the moisture are very critical in evaluating the slope stability. And the vibration information can provide insights on reasons for failure. We are also started microseismic monitoring in Joshimat now. I didn't put that data here. And use of field monitoring for landslide forecasting. As I said, for larger areas, forecasting is one of the very great tool, but it has some false alarms. So when you are developing a warning system, it's basically trust. So we need to minimize false alarms to almost zero. So there, like the monitoring plays a crucial role to when we integrate this to forecasting and monitoring, then we can build very efficient, effective operational warning system for landslides. So real-time field monitoring be integrated with rainfall thresholds and slope stability analysis so that proper forecasting and warning system is possible. So thank you so much. And this completely, I give credit to the sponsors of this project, both the case studies, and also we are also closely working with the NGO, which is called Save the Hills, who are supporting us, because in India, every region has a different language. That's another challenge we do have. So we need local people support, and Border Road Organization. So they are also doing a lot of support to us. They are my collaborators as well. And these are my research scholars who contributed. Meenu Abraham, she's a Humboldt fellow now. She'll be joining NGI. And other Kunal Gupta and Amit, they are working with me. So thank you so much.
Neelima, this was so intense and impressive. Huge monitoring efforts. Great work. I need new glasses now to follow all your slides and all the information. But this proves how much information can be gathered, and what you showed us actually confirms what Giorgio said about difference between system and solution, with all your questions and answers circling, coming back. Thank you so much for sharing your experience in India, and it was really impressive. The floor is yours, Emma. Neelima extended her 15 minutes extra, but so try to be quick. I'm sorry to say that.
No, it's okay. I've not got a huge presentation anyway. Can everyone see that okay? Okay. So thanks, Sia, for inviting me to do this today. Field monitoring and geomechanics has always been an interest of mine. I used to do site investigation, so I understand the importance of using field data and interpreting it properly. But today I'm going to be presenting some of my research from my PhD project on climate impacts on the desiccation of infrastructure slopes. So I'm just going to start off with some background to help frame the problem of desiccation on infrastructure slopes and how this is fed into the development of this research project. So starting with environmental change. So looking at the UK climate projections for the future, the report says by the end of the 21st century, all the UK is going to be projected to be warmer. We've got hot summers are going to be more common with increased hot spells. We're going to have increased intense heavy summer precipitation and increased hourly precipitation extremes. So why is this important in terms of desiccation cracking? Well, because this sort of weather pattern is going to drive the deterioration of our infrastructure slopes. And that is because the drying and wetting brought between hot and wet cycles of weather leads to crack opening and closure on our infrastructure slopes, as you can see in this little animation here. And if we're going to have longer summer hot spells, desiccation cracking is going to be more intense on our slopes and last for a longer period of time, which increases the kind of time of vulnerability our slopes are to further instability. The opening and closure of cracks alters the soil structure through time. And this is a problem because we're altering the soil structure, but we're also, when we combine this with what we call trigger events, that's when the real problem starts to establish. And what I mean by trigger events is these heavy storms that are occurring during the summer months. So if we combine cracking and open crack structure with a very, very intense heavy rainfall event, what we get is this preferential flow through the cracks, which is increasing water content faster and deeper within the soil profile and causing loss of the stabilising suction that many of our slopes and assets rely on, especially those made of clay. So now that I've kind of framed the problem, we need to kind of look at where our assets sit in relation to these type of soils. So this is a kind of a map of the high plasticity clays, which cracking is most common within, and a lot of them are localised around the southeast of England. If we overlay a risk map of what areas under the future climate change projections are going to be most at risk from this desiccation shrink swell subsidence, you can see they match up pretty well with where the high plasticity clays are in the southeast of England. So then where do our assets come into this? If I overlay our major roads and rail network on top of this, you can see the high volume of our assets which overlay these high risk areas. Thereby look at this kind of shows how important it is that we need to kind of study these processes which drive deteriorations under climate change on our assets. So, and this is just showing how these processes are already taking place. This is some recent news articles over the past couple of years where we have had these hot summers with these drought conditions on top of these heavy rainfall events, and we have lots of time constraints and pressure being put on our assets because of failure during these periods of weather. So when we were designing this research project, we had to really consider lab versus field monitoring. So in terms of laboratory monitoring, there is pros and cons to this. Some of these pros being it does allow detailed monitoring. You can isolate certain parameters and find out their contributions to desiccation cracking, and also you can investigate a lot in a short period of time. But in terms of looking at the scale of assets, it has a lot of drawbacks, which is the desiccation cracking is very much controlled by what you monitor it in. So if that's the scale of your setup, that's the type of container you use, the type of environmental conditions you put in the lab, and this all leads to quite unrealistic wetting and drying gradients, which you would see at the scale of a large scale slope in the real world. So in all, like the lab experiments are quite incomparable to the scale of real world assets. And this is just kind of showing this. So this is a test embankment site here in Newcastle, which is a large scale embankment which is being constructed. And this is the mapping of the cracks on that, which are these long linear features, which again are not just captured by that lab scale and the way water would move through this on these storm events. So that brings us to the kind of field aspects of this, which again does have its pros and cons, but the pros being more beneficial to this research project of you can model realistic drying and wetting gradients on an actual asset because it is performing as it should. It kind of visualizes all the processes together, so you're not isolating one or the other. You can see how it all joins together in the field by monitoring, and it is the true scale of desiccation cracking, so it's really what these processes are going to show. But again, detailed monitoring is more difficult, and we don't have a lot of these real size assets to be able to monitor. They're not readily available to us unless we construct them ourselves. But again, that is difficult to do as well. So from this, we decided to go for an intermediate scale methodology, and this is where this lysimeter comes into play. So it's a large scale experiment. It's 3 by 2 meters by 1 meter depth. It's got a slope embedded in it, so we can model runoff and water balance within the slope. It's been exposed to both natural and simulated climates, so as well as having a rainfall simulator installed on it, it is located outdoors, as you can see here, so it's exposed to the natural climate, so the natural deterioration with actual wind, temperature, solar radiation, all these aspects are applied to the slope. So yeah, we have detailed monitoring, so we have suction and water content sensors throughout the slope profile. We have a runoff channel and drains with tipping buckets to measure runoff and flow through the soil. And we also have a camera mount to monitor that surface desiccation through time. So if we combine this detailed monitoring with long-term monitoring, so this experiment has been going on for over 2 years now, this really will help capture the deterioration which we're interested in the slope, both through the co-location of suction and water content sensors at the same depth to form in situ soil water retention profiles and see how these change through different months and different drying periods, and the camera mount to see how the surface desiccation on the surface of the soil changes through time. So I'm going to show you a snapshot of the results here, and what I really want to point out is how we're bringing all these different aspects of this field monitoring together to really paint a picture of what's going on in the slope and really understand how desiccation cracking interacts with the climate, and then how in turn that affects how water moves through the soil and affects subsequent cracking and deterioration of the soil. So this is a 3-week monitoring period here, so where we have water content in the soil, suction through the profile, the natural and the simulated storms, which were about 52 millimeters of rainfall we applied in 1 hour to the slope. So the background is rainfall is blue, and the simulated storms is the patterns, the kind of high rainfall we applied, as well as runoff and the crack intensity factor recorded during this period. So I just want to point out that we have the natural rainfall event of significant magnitude in the yellow, and then the 3 simulated storms are highlighted by the blue. So the first thing I want to show is the fact that it's shown how our soil profile is getting wetter as we move through time, and this is matched by a drop in suction, so what we expect for these kind of conditions. And if then we take a look at what the cracking is doing and relate that to what is going on in soil profile, we can see some quite interesting things where we start off with really dry conditions. There's not much rainfall, we've got high evapotranspiration, we've got high suction, and as a result, the water content profile is quite low water content. But after we apply that first simulation, we can see that the cracks start to close. They don't close entirely, but it's matched by a drop in water content and a drop in suction. Between the application of simulation storm 1 and 2, our crack pattern managed to regenerate itself. Even though we've got higher water contents and lower suctions in the soil, it still basically has returned to what it was pre the first storm. After the application of the second storm, again, we get crack closure a wee bit more than the last time. Again, it's matched by this rapid increase in water content, drop in suction back to 0. Between simulation storm 1 and simulation storm 2, our crack pattern doesn't get as much time to regenerate because we don't have the drying conditions as we did before, and we had a lot of like small scale rainfall, so it stays quite unopened but with a very fine network, and some of the larger cracks opened. And then after the application of the last simulation, they actually still remained open, and it's not until this natural storm after the 3 simulations that the cracks eventually closed. So this kind of shows the kind of duration of time in which cracks can be open with, both in terms of we've still got high water content in the soil, we're still getting cracking, we've got low suctions, we're still getting cracking. And it's this idea that the cracking can appear even when conditions in the soil aren't very, very dry, which kind of extends that period of risk of your slopes. The other thing I'd like to draw your attention to is we can actually see the response shallowing in the sensors as the slope becomes wetter, which kind of shows these cracks closing from the bottom, and this idea of preferential flow in action in our slope captured quite well. And then the last thing I just want to point out, which is interesting, is we don't get runoff on the slope until after that natural rainfall event, and this kind of shows the sheer volume of water that a cracked slope can take in before it generates runoff, which obviously has major implications for developing weak zones at depth if we're allowing all this water to ingress into our slope. So one other thing I said is we can help see the degradation of the soil through time through our developing in situ soil water retention curves. So this is the drying curve from the summer of 2022, and we compare that with the drying curve of 2021. So we can see we have a shift in the soil air entry value, and we've got an increase in the saturated water content, and we have a steepening of the gradient, the desaturation gradient. And this kind of points towards development of a larger, more open connected pore structure, indicating this deterioration of the clay through time. And it's not been able to maintain and sustain as high suctions from over the course of just one summer. And relating this to, again, this is from this on-site large-scale field embankment in Newcastle. They also plotted their soil water retention curves from different drying events, and they also captured this decrease in the soil air entry value and this increase in saturated water content, which just shows the ability of this kind of intermediate scale experiment to capture well what is happening at a field scale. So just in summary, so desiccation and just instability is a growing concern to our infrastructure asset management. Field scale investigation is crucial for our understanding of how cracks form and how this affects the hydrological profile through the slope. Small crack intensities can still accept a large volume of water, which has implications for the stability of your slope. And microstructural degradation is occurring through across these dry-wet cycles, affecting these suctions, which a lot of slopes rely on to remain stable. But thank you for listening, and I'd be happy to take any comments or questions you have.
Emma, this is great work.
Thank you.
So from Neelima of huge monitoring the Himalayan mountains to a small scale monitoring. But you know what? This kind of research is showing that monitoring is not just measurements, but putting together all this information with the camera and the observation is the solution. It makes you feel it, not just see it. When you see it is something, but when you feel it is when you can really find a solution to the problem. Thank you very much for sharing your research. Wish you the best.
Thank you.
I don't know if Giorgio wants to add something before we close this.
Just one comment related to what Emma just presented and what you said, Marc. What Emma has presented is a very good example regarding the fact that field monitoring needs for a strong, let me say, theoretical or laboratory support in order to understand the measurement. Otherwise, again, if we keep the 2 points separated, if we don't integrate different knowledges, we cannot reach the final goal. So it is important that we can rely our information, our measurement on very strong theoretical basis. And what Emma has presented is a very good example of this.
Yeah, just to add to that, like I think that kind of larger scale experiment has helped inform smaller scale experiments we have as well. So we're taking what we see on that and taking it into a smaller scale to help back up what we see at that kind of larger scale. So it is really having like that play between both small scale and large scale, which has really helped understanding what's going on better for me anyway in my research. Both are playing a really strong part in framing the problem and understanding it.
The very last comment, you, Marc, said that we moved from Himalaya to a small area, and this is exactly what I tried to present in my presentation with the zoom in and zoom out. So we have to look at the broad area and to the detail in order to understand what is happening and to be prepared to react to what is happening. So very interesting presentations. Thank you, Neelima. Thank you, Emma.
And thank you.
Yeah, really, thank you. I want to add something that even though field monitoring is one technical committee out of 40 at the ISSMGE, it's a huge field. I mean, we didn't even have time to talk about the measuring devices, the latest technologies such as drones catching the surface to predict landslide activities. We didn't talk about the latest fiber optic cables in, real-time data collection and the latest data acquisition systems. But this is the time we have. Sorry for our viewers. Please contact one of our experts if you have questions. And ISSMGE is an open access with hundreds of papers and proceedings on our website. And if you visit our virtual university, you also have hundreds of webinars and free lectures open for everyone. Thank you so much. I will end this lecture here. And thank you all for the speakers for participating and your support.
Thank you very much.
Thank you.
Thank you so much.
Bye-bye.
Bye.
Bye. Thanks, everyone.
Bye.